Hey, so I figured out the question. I had to go and do Professor Frieden's example question in order to figure it out, which happens with a lot of my stuff. So I'm learning new things too, despite the fact that I've been doing this for, a few years. So the first thing I did was I wrote out the lower class limits and the upper class limits given to us in the question. And then the question that I'm doing right now is section 10.1, question 17, which is on page 535 if you just want to go look there for reference. It is a question about test scores to see if the frequency distribution is normally distributed. So I copied all the data, the frequency and the lower and upper class limits. So the first thing I did was I calculated the midpoints. What I did was I did the average between classes, and then when I ran out of classes, I did the lower class limit and the upper class limit. But one thing that was kind of weird about this was that they made the lower class limit the upper class limit of the next class, which is not typically something you do. You usually want to like separate it by some value. So if I were to rate this person's histogram, I would give it a 3 out of 10. But anyways, so the next thing I did was after I calculated the midpoints, what I did was I put the frequencies next to it, which was given to us, and I took the sum of the frequencies, which is our n that we'll be using shortly. The next thing we need to do is calculate the mean and the standard deviation in order to continue with the problem. So the way you calculate the mean is you do the midpoint times the frequency. You get those values like you see here. You sum them, and then if you go to my mean, you do the sum of the midpoint times the frequency, and then you divide by the total frequency, which is your n. Okay, and then next to calculate the standard deviation, this is the way I showed you in class, which was the square root of the mean. This is not a good way to do it. When I tried to do that same theory on a different question that was like this, and it didn't work at all. So I would advise against using that. It worked for this case, but not in other cases. So I would advise against that. So I'll show you how to do it the correct way. So the first thing you're going to do is you're going to do your midpoint minus your mean, and then I made that the mean a permanent cell reference, so then when I dragged and dropped, it didn't move anywhere, so you can see there. The next thing I did was I squared each of those values, multiplied each of the values by their respective frequencies, and then I divided by the degrees of freedom. Then when you sum that, you get your variance, which will turn out to be 69.5, and then square root that number to get your standard deviation. Right there. And some housekeeping. Step 0, the null hypothesis is that the variable is normally distributed, and the alternative hypothesis is that the variable is not normally distributed. There you go, alpha is 1%. Okay, and then next we're going to calculate the left tail area. So the way we're going to do that is we're going to use our norm.dist that we were using back a long time ago. When did we use norm.dist? I think it was in like chapter 5 or something like that, like half a semester ago. So yeah, that was a while ago. So for our x, we're going to plug in our lower class limit, and then if you see, I went up another lower class limit. So then the area underneath each little sliver would be able to compute, so I'll show you that next. So with that, you insert your x, which is your lower class limit, your mean, which is right over here, and then your standard deviation, and then whether or not it's cumulative, I put yes for cumulative. Okay, and then I repeat that with every class limit. And then this one, I did an extra one, so then I'd be able to subtract to find each sector area. There you go, and then to subtract to find the sector area, you'll take the next highest sector area minus the one below it, and then that will be like your lowest sector area, and then you just keep going up like that. There you go. And now you see why I had to have the extra one, because I needed a way to be able to subtract the highest one minus the lowest one. Okay, and then after that, we will multiply this sector area by the frequency, which makes sense because if you think about like the standard normal curve and like the sliver of area underneath that, if you multiply that by the total number of values you have, then that will give you like the expected frequency, right? How much you expect to be under there in like ideal conditions if it were perfectly normally distributed. There we go. And then next, what we do is we do our original minus expected squared divided by our expected, which should be looking pretty familiar to you guys. And then we sum that here at the bottom. And then that will give us our chi-squared test statistic. Then to calculate our critical value, we'll do chi-squared.inverse.right tail with our probability, and then we're going to use 2 degrees of freedom, and then that's because we have to subtract away 3 degrees of freedom because of how many variables we were given, and then standard you will, sorry, yeah, you'll use the 2 degrees of freedom to get your critical value because mathematicians typically subtract 2 degrees of freedom from each one. But the book has you do 4 degrees of freedom. Either or works fine. There you go. Sorry. 0.73. There we go. That's our correct p-value if we're comparing it to this critical value. If we're comparing our p-value to the 13.1, it will be equal chi-square dot dist dot right tail. Then going to have our x, and then our degrees of freedom, which the book had listed as 4, and then that would be our p-value if you're comparing to the 13.27. There you go. So our conclusion is that we fail to reject the null hypothesis. There's not enough evidence to prove that this distribution is not normally distributed. Yeah. And that's everything. It's kind of really complicated and long, and this is not on your quiz, but it is fun information to know in case you ever are held at gunpoint and your kidnapper wants you to figure out whether data from a graph is normally distributed or not, I guess. But yeah. That's the chi-square goodness of fit test, and hope you guys have a great day. See you later. Bye.